We're finally not looking at an airplane in this problem. We're looking at something similar to a margarita glass, and we're following this point P here as it goes in a circle around the glass, and the length that P is along R is given in this nice equation here, and we're given information about this angle beta and this angle theta. We are to find the magnitude of the acceleration at point P at the time where the velocity along this r-axis is maximum. Now let's take a look at the angles that they've given us. At b equals 30, we're given that the value is constant. When the value is constant, you know that b dot and b double dot are equal to 0. Likewise, when theta dot is constant, you know that theta double dot is also equal to 0. And that's going to be really nice later because we can plug in 0 for the equations and it will simplify them down a lot. Here at this r, we're given information about n, and you can just plug that n value into there. Now, we're using spherical coordinate system equations to solve for this, and we'll get to that in a second, but if you know you're using spherical coordinate system equations, you know that you have to redefine this beta here, because that angle beta is not along the spherical coordinate system. If you were to redraw this vertical line over here, and then pretend that it's along a XYZ coordinate system, you have R going along this way, then you know theta dot is going around in that direction, just like theta does, but our beta angle is here. And from the problem before, we know that that angle is not along the spherical coordinate system, but you know that phi is. So what you can do is you can subtract b or beta from 90, and then you get phi, which is something that will match all of your equations later on. So therefore, we're going to change this and define it as phi equals 60 degrees. In a problem previously, we looked at the different components of acceleration. And in these components of acceleration, you can find them in the book. I'm not going to derive them because I don't find these quite as helpful as the other derivations that we've done before. But know that a of theta, a of phi, and a of r have associated equations based on the derivations of those positions. And for r, we'll also use the equation that's given to us before because it is not constant and it's going to change as it goes along. So, let us first look at the acceleration of r. And we will determine that using that equation. And I went ahead and plugged in that n here. And let's get dr dt, which is 0 plus 200 pi times cosine of 4 pi t. And if we went ahead and solve for acceleration, we would get negative 800 pi squared sine of 4 pi t. And we are looking at VR max. At VR max, you'll find that the cosine 4 pi t equals 1 and sine of 4 pi t equals 0. Well, here is a 4 pi t, so knowing that at this particular moment in time, this 4 pi t equals 0, then this whole equation is 0, and you get that your r double dot is equal to 0. So, let us pull from equation 219, which is AR equals r double dot t minus r d phi dt squared minus r d theta dt squared cosine squared of phi. And since we know some values are 0, it's going to make it a lot simpler. We know that this is 0, and from the information that phi dot is constant, or that phi is constant, we know that d phi dt is 0. So this is much, much simpler, and we'll find that it is 0 minus 0 minus 200 plus 0 times 4 pi squared cosine squared of 60, and that all boils down to negative 80 pi squared millimeters per second squared. And that is AR. So now we have done AR. Let's move on to A theta. The equation for A theta is cosine of phi over r times d dt r squared d theta dt minus 2r d theta dt times d phi over dt sine of phi. Well, that equals 0 because phi dot equals 0. So this is much simpler. Now if we multiply this out, get d theta over dt times cosine of phi minus 0. Plug in what we know, we'll get 2 times 200 pi times 1 times 4 pi times cosine of 60 degrees minus 0. And that all boils down to 800 pi squared millimeters per second squared. And this is now the second component of acceleration. Now let's look at this third component. Acceleration of phi equals 1 over r times d dt times r squared times phi dot, which we know that equals 0, so it's going to simplify it down a lot, times r theta dot squared times sine phi cosine of phi. And simplifying that as well as plugging in the values, 4 pi squared sine of 60 and cosine of 60. All of that simplified down equals 800 times the square root of 3 pi squared millimeters per second squared. Because this is a vector, you can take the square root of the sum of the squares of each of the components, and now you can find the magnitude of acceleration at the max velocity, and that will be 17.66 meters per second squared. And that is using the components of acceleration and the values of r and theta to get phi and theta.